Imagine how our crops could be so efficient if these roots were able to maintain their functions. Plants eat through the roots. These tiny, adventurous, and powerful thread-like structures extends and explores the world beneath them, looking for water, nutrients, dissolved minerals, and gases essential for plant productivity. However, this is not always the case. Roots are challenged by various abiotic and biotic constraints in the soil, with water status of too much or too little being a major factor leading to plant stress. Climate change has increased the intensity and frequency of flooding, triggering severe crop losses, aggravating food insecurity and hunger. Enough water is a prerequisite of normal plant growth, but saturation of the soil water holding capacity, or even supersaturation, easily leads to flooding stress. Roots absorbs oxygen from the air spaces in the soil, and when these air spaces are filled with water, movement of gases within the soil is hampered because of the very slow diffusion. Thus, there is oxygen deficiency. This lack or absence of oxygen restricts roots from respiring. Thus, there is only a limited amount of energy produced for nutrient and water uptake. This results to plants with low performance and low productivity. However, flooding stress has triggered a diverse adaptive mechanism in plant roots and shoots at the morphological level to help them escape hypoxic environments or improve oxygen diffusion in submerged organs. There are tomato varieties that are able to produce advantageous roots under flooded conditions, and this has become one of the determining traits for its tolerance to flooding. Advantageous roots emerging from the hypophyll, from the base of the plant, plays a major role in maintaining its metabolic cycle, including photosynthesis and respiration, allowing the plants to grow and develop normally. These newly emerged roots are physiologically adapted to poor aeration. It contains aerenchyma, a highly porous tissue that improves the diffusion of gases within the roots, thus enabling the energy-dependent activities of the soil to resume. Moreover, these roots could also replace the old root system that died because of hypoxia, assuming its role in nutrient, in gas, and water uptake, allowing the tomato plants to survive, to grow, to recover, and to remain productive under flooded conditions. This adaptive root mechanism is not just a simple plant mechanism. It involves several processes and interactions. Ethylene accumulation in flooded tomato plants has been linked to the formation of adventitious roots. Endogenous ethylene entrapment by the surrounding water serves as the first signals to a plant, signifying that there is a change in gas composition around the root environment. Moreover, this ethylene buildup helps in the regulation of the LE-XP1 gene in tomato, an expansin gene that allows cell wall loosening. And this loosening reduces the resistance, the mechanical resistance of the stem tissues, and favors the emergence of new roots. There are still processes and interactions that we need to uncover and unravel for us to understand the advantageous root formation in tomatoes. In the context of global climate change, waterlogging has become a major constraint in agricultural production. Root adaptations as well as root-related traits and characteristics, is an important area that we can exploit to help us develop crops with novel roots better adapted to both abiotic and biotic constraints in the soil. An in-depth understanding of the root system development and function, as well as an identifying root traits that contributes to crop productivity amidst various scenarios, is a research frontier that might enable a second green revolution needed to sustain world food security.